Okay, I hope you're looking at my R Studio screen, right?
Yes.
Perfect. Okay, let's begin. Today's session is all about logistic regression, and also called as logistic regression. And why do we do logistic regression is a question. Right? In the initial case, when we were working with linear regression, we were predicting um, maybe a weather outcome or the crop growth, and they are all numerical outcomes. And since they are continuous data, and we were predicting it. In case some of the times what happens is that we will predict whether some of the event is going to happen or it is not going to happen, whether my customer will buy a product or he will not buy a product, whether she or he will sign up for a credit card, or it's like will they renew the subscription that they did for Netflix, or will they buy my product based on the promotion that I'm doing, right? And here we are just having two outcomes. One is like either they buy or they do not buy. Right? This is the case with most of the times, like when you're a manager and you're supposed to take a decision where I am supposed to give a loan to the person who applied for this particular, for doing a business. And as a bank manager, you have a say as like yes or no. And this is a bit difficult when it comes to uh, modeling, right? And the standard linear regression models cannot really work. Why? Because you're just having two probable outcomes. Hence, what we do is like we'll basically get into the next level of modeling that is called as logistic regression. In the logistic regression, we can predict the outcomes, and we'll be predicting the probability of the outcomes based on some metrics that we have. Okay. If you go down in the R Markdown file, you can see there are like a lot of information given here about logistic regression. And the core feature of this particular model, or like logistic regression model, is that it normally relates the probability of an outcome to an exponential function of the predictor variable. So what do they mean by it? Here, they will just estimate the probability based on the n number of predictor variables that you're going to take. Okay, the predictor variables that I mean is the independent variable that we discussed last week. And some of the variables that we are collecting, for example, say if you are a bank manager and you're trying to say whether to provide loan or not to provide loan, and this is a probability whether he's going to get or he's not going to get. And the probability can vary from, in general, you know that the rule of probability is that it can vary only from 0 to 1. And hence, the chance of, the probability of getting success in an application of a person who is like trying to get a loan, it might be more than 50% or less than 50%, or it's like it might be near to 1, right? And if the probability is lower, and then the chance of getting the loan is also lower, right? And how this probability is predicted, it's predicted based on his past records, like whether he has got a loan from some other banks. And also now we have, in India, we have a score called credit rating score. And then we'll also take the information of credit rating score. The credit rating score is basically an outcome of different loan transactions that you had in the past. And these data will be taken to predict the probability of whether you will get the loan or not. Okay. And also one different variation is that in terms of when you're producing a linear model, the responses will basically vary from infinity to minus infinity to plus infinity, in a sense, because you are having a continuous number. It can take any number of any values from like between these infinities, which in case it cannot really happen in the probability, because the maximum range or like minimum range it goes like the minimum range is 0 and the maximum range can go as 1. And this also puts in another constraint in our model building, and the constraint is that you cannot use this minimizing the sum of squared errors in case of logistic regression. Right? The last class we saw that we are supposed to reduce the sum of squared errors because we are fitting a ordinary least square regression. And the ordinary least square regression cannot be performed because this is all about estimating probabilities, and the variance is not really high, and then also the data is not really distributed normally. Hence, we cannot really use the least square method. And if you are able to get the understanding of why we are just using probabilities and also why cannot use least square method, then let's move on to how this logistic regression generally works. Okay. In general, what happens is that either you can normally get two kinds of values from logistic regression, and if the p-value is 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 near to zero, right? And what happens is that the probability of occurring having an event is somewhere around it's not going to happen, and somebody who applied for a loan cannot really get the loan. And if he's just nearing to one, and basically can get the loan. Okay, and that's what I mean here in this line number 38 of this RMD file, where it says that the errors of this logistic regression is depends upon the p-values. Okay, and hence it is also reflecting in terms of like replacing aspect with as related to least square method. And here we will just basically look at the errors, and if there is a larger variance, uh, it is basically like you have larger variance when you are approaching 0 or 1. Okay, and don't worry much about this in terms of like working in terms of logistic regression errors, but we'll understand how things work when it comes um, to, to interpretation. Okay, let me also show you a small image. I think that is not available in the RMD file, but I can show you here, because that is really important to know why this error cannot be computed, or like what we did with logistic linear regression. Let me go for a new share. I hope you're able to see this graph now, and this can be incorporated in RMD file, but I didn't do it. And now you can look at that. What happens is that your observations can only take two values, right? So when I talked about logistic regression, I told you that you get a loan or you do not get a loan, right? And if you're not getting a loan when you're applying, it means like you are basically having zeros here. These people are the ones who did not get the loan, and the ones who got the loan is here. And now what we can do, we cannot really look at any sort of errors, right? So in terms of if you ask any person, right, and to say, okay, can I find the error? Can I find the deviance with this model? But we cannot really do it, because in the linear regression, you'll have a straight line here, and your observations will be scattered across the plot, where you can look at how this fitted line is differing from the observations, where you can find deviance. But here it is not the case, where you cannot really find deviance. So hence, it's becoming difficult when it comes to logistic regression. For example, say, imagine there is a person who has a monthly income, it's like a net profit value of his company. Imagine that is like minus $400 million and minus $200 million, and it's like basically these people are at loss. And here people are like at the break even, and some people are making $100 million per annum, and there is someone who got like $600 million. Okay. And what happens is that if you look at when they are earning at the less, or like if their profit is low and then the loan is rejected, but if their profitability is high and they are getting more loan, and which means like if you are having a break even and still there is a chance to get a loan at 50%, right? If you draw a line from here, if you move from 0 to the top, and if you look at where it dissects, and now from here you just move on to this side. So there's like at least somewhere around 50% chance to get a loan if you are just breaking even, at least. And if you're making more than $600 million, and basically your probability is too high, it's just near to 1, somewhere around 99% or something. Okay, I hope now you got why we cannot really compute errors, and also how this logistic regression works. Okay? The logistic regression normally takes a sigmoid curve, or like a S-shaped curve, and this S-shaped curve decides the probability of any person who is applying for a loan, or it's like any person who is like saying yes or no uh, um, to the decisions that they want to take. Okay, let's go back to the R&D file and try to understand a bit more of logistic regression. Okay, and Now, we will normally get some sort of outcomes from this logistic regression. Right? When we looked at the linear regression, we know that the coefficient and other things will basically reflect how it's going to influence the outcome variable. So if there is an increase in 1 unit of x, and that's going to increase 1 unit of was like maybe 2 units or 3 units of uh, y variable. Okay, because we saw that, imagine that the beta value is somewhere around 3, and which means if you have increasing x by 1, and it's going to have an effect on the outcome variable by 3 times. But this is not the case with logistic regression. Why? Because this is just talking about the probability, right? How this probability is going to be affected by your um, your beta values. And hence, there is also a bit of trick behind this logistic regression, because we are basically using the linear regression and then trying to convert that into a logic regression and predict the probability. Okay, so what we normally do is like we normally have a data, normally have an equation, and the equation will be like y is equal to a plus bx, and that's the beta, or it's like a is the alpha, right? And or it's like in the other terms that we learned is like beta naught and then plus beta 1, right? And since you want to predict the probability and you want to see how this is going to change, and you want to fit that one to the normal linear regression model, you will normally take a log on both the sides. Okay, so when you take a log on both sides, and this probability can be predicted with a normal linear regression equation. Okay, so how will you predict? In a sense, let me see if I have some sort of example, uh, to show you the formulas. Think. Okay, so there is a little bit information here. Okay, so now I could find one. Okay, so it's not available at the moment with me, but what happens is that, for example, say you let me type it in the RMD file here. So you have a look at the RMD file, line number 59, where I'm typing, which is not available in your system, where I say y is equal to a plus bx. That's the normal linear regression formula. What happens is that now I need to take a log of y, and that's how I can fit fit this probability values, right? And when you take the log of on both the sides, okay, so what happens is that later on when you're trying to interpret the model, you're supposed to count this log of a log function as well, okay, which we'll talk a bit later. But now at the moment, what happens is that in general, when you're working with this formula, and since you're having the outcome as a 0 or 1 in the y case, what happens is you basically try to predict the probability of the desired outcome, and then the probability of not getting the outcome. So it is like 1 minus b, right? And that is how it will get transformed. And then you will basically have the exponentiated uh, form of your alpha and beta values here, like the constant, and then the it's like beta naught and then beta 1 values here. Okay, and still it will also have the error term associated with it, as we discussed last class. Okay. So what we are trying to predict, so we are trying to predict saying like the probability of having the outcome occurring, or if it is not occurring, what's going to happen, right? And that is what we are doing, and we are able to fit that into the linear regression model by taking log on the sides. Like, and this information is important. Why? Because when we are trying to look at the coefficient values that we get out of the model, and we are supposed to exponentiate it to interpret it. Okay, and we'll also see that in the when we perform the model on our own. Okay. Now, if you look at the interpretation of coefficients, as I told you, since we take log on both the sides, we cannot really use the normal way of interpreting. We don't take the coefficients as such, and then you're supposed to exponentiate the coefficient because you're taking the log. Okay, and if you're pretty good with how the log and other things works, and then you'll be able to understand why we are exponentiating. Okay, and when you're exponentiating the function, and if you're getting some values out of the exponentiation, and if the value is more than 1, and the probability of having that event occurring is positive, and if the value is less than 1, and the probability of having that event occurring is negative, which is not going to happen. Okay, and which you'll also see from the results that we are going to look at. Okay, now you can work along with me and try to understand how this logistic regression works. And still, if you have any question in terms of understanding the model, please let me know. Any questions?
Adam, no.
Okay, perfect. So, which means like you are able to understand why we perform logic regression, and also you understand the basic nuances. Like, okay, so there are a lot of things that we can do with logic regression, because there is something called as probit regression. There is like multinomial logic regression. We are not talking about that, right? But you can basically get into that area. But if you understand this basics, and let's go. Like, which part should I explain? Like, okay, so probability of so p of 1 by 1 minus 1. Right. So now, as I told you, we basically have two outcomes. One is one indicates that you are no, it's a positive outcome, right? So you got a loan. Right? That's like if you're saying 0, you did not get a loan. So no loan, right? So it's a negative outcome, and you did not get a loan. Right? And hence, we are trying to predict probabilities, right? We are not predicting whether it is 0 or 1, because we already got the information from the data. Right? The data will basically say that, okay, this guy got the loan and this guy did not get the loan. But we are predicting probabilities of the outcome. Right? Imagine if there is one other guy coming in and then asking, like, I need loan. And he provides the data like, okay, and this is my income, this is my repayment methods in the previous case, and now you incorporate the data into the model, and then the model will say whether to provide loan to this guy or not, and that estimation will be a probability estimation, not the actual outcome. It will not say 0 or 1, because that is really rude, right? And we are now just predicting the probability, and how we'll predict probability. And we are basically taking the normal linear regression equation where y is equal to a plus bx, right? And since we cannot really fit with just y is equal to a plus bx, and when we are estimating probabilities, when we need to convert this 1 and 0 as a continuous number, right? For example, say 1 and 0 has to be converted into a continuous form, which is not the case. Like now it looks like a kind of factor, right? So what we do is like we take log on both the sides. And when you take a log, what happens is that this equation, when you're substituting with like probability functions, and it will basically try to say the P is the desired outcome, which the person is expecting, right? And 1 minus P is the negative outcome, right? So if you just substitute P with 1, basically it is 0, right? You understand what I mean? And if the odd of the event, right? If the odd of the event becomes larger, and the probability of the outcome will basically become lesser. Yeah. If it is lesser, and then the outcome will become larger. And that's what I mean here. It's like P minus 1 by P. So the P represents the probability of the desired outcome, and 1 minus P represents the probability of the outcome not going to happen, since it's going to be negative. Right? And I hope this clarifies your question. And let me know if it is sorted. Okay, good. Now let's get into action, and let's work on this model, right? So load packages that is required, right, and also load the data, right, And let me perform it because since you are going to perform this for the first time, especially in terms of logic regression and other things. And I also have one other example where you perform and then you interpret the data. Okay, so let's perform together, right? So you also have your RMD file open and work along with me. Maybe if you don't have two screens, it will be difficult. But now maybe just listen to me and then start typing. Okay, I'm in the basic setup chunk in line number 70, right? And I am loading necessary packages. We don't really need any special packages for logistic regression, and that comes from the base R. But however, for subsetting and for manipulating data, we need a dplyr package. So we'll load dplyr package. And also to produce a graph and see visualize the data, we need ggplot package. Okay, so run that. And then the data that is uploaded is here. So I need the data as well. Okay. And now have a look at the structure of the data and say structure my data. And now you can see admit, which is which has values of 0, 1, and 1. And what is it? Is it the DV or is it the IV? Is it the dependent variable or the independent variable? And identify the independent variable and dependent variable from the data, and let me know which one is put in the chat box, or like maybe you open up your mic and say which one is the independent variable and which one is the kind of non-dependent variable out of your insights that you got from the data. Can you say what could be the independent variable, what could be the dependent variable?
I guess GRE and GPA would be independent.
Yep, and also rank.
Oh yeah, rank as well. And
Yeah,
admit would
rank
be
also,
the dependent one, and higher the GRE, GPA, and rank, the possibility of getting admitted. More or less.
yes. So
Roughly.
this data is a kind of a fictitious data, though it's kind of for just for an example, right? And this basically tells there are 4 variables. Okay, don't think about like x. X is not required for analysis. That is just row the row information, right? And admit is whether the person who applied for the college got an admit or not, and based on his GRE or GPA. GRE is the score that you normally the competitive exam score. I was like aptitude test score, and then GPA is the your undergraduate GPA, right? Was like your school GPA, and then the rank is for from what kind of college that you study. Whether you study in a top ranked college, in tier 1, tier 2, tier 3, tier 4 college. So there are 4 categories here. But now we can see some sort of problem, right? So we need to clean the data a bit. Hence, you use dplyr to select only the first 4, sorry, the second, third, and fourth, and fifth column data, and change the rank data as factor, and also change admit and GRE score as a numeric data, right? Which it's not required, right? Though system will understand that as a integer can also be treated in the model, but still I think it is better to get back to the basics and then try to work with that as well. Hence, change that one and fix it. Right? And once you're done, and put a thumbs up or like put a S in the chat box that you're done. And let me know how you progressed. Okay, so I got perfect. I would recommend everyone else also complete, like two of you, Swati and Venkat, can also confirm once you're done with that. and you need to store the data somewhere, right? So maybe just use my data and say like my data, reassign my data, say my data, and start your deploy comments from here. If you're still struggling, yeah, because I'm also teaching for the students here in the university, and they need each and every steps to be deciphered, and since they want each and every single thing to be explained, and I assume that that might be the case here as well sometimes. Okay, so I think Anirudhan can explore the visualization of the data and try to get the output of it and see how it is printed out. And I'll explain to you a bit later about the methods and the arguments that we used in the code. Okay. And also use try to use scope function as like the mutate at or as like mutate all function, or even I think for this particular task, I think you can use a mutate if function and then complete it faster, because we haven't really worked on those kind of scope functions, but it is really useful when it comes to data manipulation. And also ensure that you loaded dplyr, right? Some run the previous chunks, complete the task in the previous case, and then work on it. Okay, so do we have to wait for more time? Can you just confirm here in the chat box? Okay, so let's see. We are getting some information. Done. Perfect. Amazing. Okay, let me also complete in my side. I hope you did the same. So you select admit. This should be like 2:5, that's like 2:5, right? And then say mutate the rank is equal to as dot factor rank, yeah, and then say mutate if as dot integer, like is integer, because if that is integer, as dot numeric. Okay. It's expecting one set formula. Sorry, this is extra brackets here. Okay, now let's have a structure of the my data. Now you can see we have successfully converted few things in the sense we have admit in numeric, GRE and GPA also in numeric, and the rank is in factors. Okay, and what is the reason that we converted rank data as a factor? Any ideas or opinion on this particular point?
Yeah, we have only 4 levels, right?
Yeah.
Fixed 4 levels.
Yeah, like we have 4 levels. I understand that, right? But initially, in the first case, right, we had it as integers, right? And we converted that as a factor with 4 levels. Yeah, I understand, right? So, what will happen if I don't do it?
Could be considered as a value.
Yeah. So what happens when it produces a model and it will just have one value? Okay. But when you convert this as a factor, what happens is that now it will compare and contrast these 4 different levels of college in the model. So when you are getting an output, any of the college will be taken as a base, and from that, all the other colleges will be compared, and then you will get the results. Okay, let's have a look at it, and you'll get more clarity when we go on that, right? And when you want to visualize the data, right? So it's quite simple, and we are using the ggplot function. And to extract the data points, we are using geom point. And to get the curve, the logistic regression curve, we use geom smooth. And there are subtle changes here. Normally, when we plotted for the linear regression, we used method is equal to lm, and we did not really add any method arguments, but we are adding method arguments is equal to list family binomial. So binomial represents the outcomes are 2. It's either 0 or 1. Okay, and also I set the standard errors as false, which means you will basically will not have the standard error bars around the line. Okay, and try to manipulate and change this arguments and see how that works. Okay, when you plot it, you'll get in. What is GLM? So GLM is called generalized linear model. Okay, and generalized linear model is the base for ANOVAs and also for these kind of linear regression models, logistic regression models. So there is linear regression models, and that is where we use LMs. And there is something called generalized linear models, and especially they work for categorical data. And for example, say ANOVA, we may not really for example, software engineers or the data scientists normally do not really work with this kind of ANOVA stuff, but they do also need sometimes. However, largely people work with in terms of machine learning and then data science. They normally try to build models. When they build models, they need to know whether that's a linear model or it's a kind of generalized linear model. And these generalized linear models are for some sort of categorical data nature. Okay, so you're trying to compare between groups, and you're trying to compare zeros and ones and stuff where you use GLMs. Okay, I hope that clarifies. Now, if you look at the graph, and now you can see as and when the GPA increases, the probability of getting admission also increases. And you can see if you're getting a 4.0, and the probability of getting admission is somewhere around 50%, right? It's somewhere around 46% or something. Right? But you can also see, even though if your GPA is somewhere around 2.5, you still get admissions, but the probability is low. Yeah, the probability of getting admission is low. Right? Why it is happening? And in this case, why a guy who got a GPA less than 2.5 also gets an admit? What's the reason? Just as an imagine.
Maybe some other factor contributed to it apart
Perfect.
from GPA.
Yeah. So you have you apply with different other aspects, right? And based on that, they will take a decision. Like now, try and plot for GRE, right? And also we have GRE score, right, of people. And let's see, is it? Yeah, it's the same notation. And let's just try that one. Yeah. So even with the GRE score, we are getting. If you are getting higher GRE score, it basically increases the probability of getting admission, right? It was 46% in the earlier case when you are having your highest GPA, right? 4 out of 4. But for this one, like if you're getting 800 out of 800, the chance of getting admission is like quite high, right? And apart from this, the way that you explain your cover letter, the way that you explain, have your extracurricular activities, and that will increase the chance. Okay. I hope this gives you a bit more clarity on how to work with these kind of decision-oriented models. And now let's build model. Okay, so let's start with this one. I'll do this particular model, and later on you can do on your own. Okay, so there is one more example where you are going to perform on your own. I'll leave it to you, and if you're we'll all sit together and then complete the task. But still, because it is important that you understand the models and then understand the outputs of it to get more clarity, right? Now, instead of GLM, we'll use GLM. And you know that we are trying to predict admit with informations like GPA, GRE, and then rank, right? That's the rank, rank. And here you need to say data. So data is from my data. And then you need to define the family, which was not, which you did not declare earlier in the case of building linear regression. But here you need to specify the family, because in the family you also have like binomial, and in the binomial you also have logit and probit. Hence you are supposed to say binomial. Let's say binomial, and you also know that how to extract information from models, and it is the same with in case of logistic regressions. You take a summary of model 1. Okay, now I would ask you to interpret this information. Okay, now tell me what do you understand, basically what do you understand by this information? Perform similar operation in your system, right? And also get the output. Now tell me, after looking at the output, just tell me what do you get from this information. Because this is a bit tricky compared to the earlier case, because we just had LMs, and in the LMs we did not really use kind of categorical data as a predictor. And here rank of college is a predictor, and you are getting output like rank 1, rank 2, 3, 4, but not rank 1. And also you're getting score for GPA and GRE. Right? So largely as a programmer, it's always easy to do stuff like you just code things and then get the output. But the problem is like how to interpret the output. That is where we normally we are supposed to know that one if you want to really scale up well in the data science arena. Okay, so now tell me if anyone has an idea on this, please open up your mic and say.
So I have some idea.
Yes.
It seems GPA, GRE, and rank to have higher errors. Also 50%, not 50%, but then 0.05% of. I'm not sure if they are errors, but then let's say they can't be trusted a lot as much as the rank 3 and 4.
Okay, so nice. Okay. So any other opinion? What do you feel, Venkat?
Yeah, Bala, for rank 3 and rank 4, there is a higher chance of getting admit, and it has less error term.
Okay. Okay, so
Yeah.
Swati, what do you feel about it?
I agree to them. I don't know.
Okay, so this is actually called as like getting along with the group.
Yes.
Called herd effect.
Yeah, one small thing.
Yeah, please.
I wouldn't actually say rank 3 and 4 provides higher chances of getting admitted, but then we can't trust rank 2 as much as we can trust rank 3 and 4 data.
Okay.
Yeah.
Yeah, so you cannot trust rank 2 score compared to 3 and 4. That's what you mean, right?
Comparatively.
Okay, right. Okay, let me provide you an explanation of how to really get into this interpretation part. Yeah. First, look for the p-values. Okay. And you should always get the p-value less than 0.5. Okay? In here, in all the cases, we are getting p-values less than 0.5. Right? And you can see that is it's a single star which is less than 0.05, which is a good sign that all the predictors that you used in the model predicts the information. And next, you need to go for these estimates. Look into this column. And intercept is the constant, right? Which is basically, if you don't have any information of the predictors, what will happen to your admissions? If you do not really provide any of the information, and it's going to negatively affect your application, which means you will be rejected. Yeah. And the GPA has a higher influence on your admissions because it is 0.8 higher score, right? But GRE plays a minimal role. That's what they mean here. And then rank 2, 3, and 4, this has to be interpreted carefully. So please listen to this one carefully, right? Now you can see rank 1 is not there, but we have rank 2, 3, and 4, which means you are actually benchmarking this model with rank 1 college. And if you're studying from a rank 1 college in your undergrad, basically you have higher chances to get admissions. Why? Because if you look at rank 2, 3, and 4, they are in a negative phase, which means the probability of getting admissions if you studied from rank 1 college is higher compared to rank 2, 3, and 4. And that also, the probability of getting admission decreases as and when the rank decreases as well. So rank 2 is 0.67 minus, that is minus 0.67. So which means you are having a 0.67% chance less than the rank 1 college if you are studying from rank 2. And then it goes to rank 3, still increases, and then rank 4 still increases. So rank of the college, if you're undergraduate college, play a major role in your admissions. Okay. And if you're trying to get an admission in the college, in the US college, this data is kind of a teacher's data. So, but still, it helps you to understand how the rank of the undergraduate college play an important role in getting admission for the master's degree. Is it clear now? Right? But still, what happened here is like we are trying to interpret the log values rather than the log odds values. Okay, so what we are supposed to do is like we are supposed to exponentiate it. Like you need to take the log out of the equation and then try to interpret the data. And for that, what we do is like we use exponentiation of this coefficients. Okay, and let's see exponentiation of COEF. COEF is the coefficient of the model. Trying to extract the coefficient of the model. You say model dot 1. And now you got a very good picture of your data. Okay. Now you can see which have a higher impact on your decision, right? As I told you, right? So when you're trying to interpret the coefficients, you are basically supposed to compare with number 1 in terms of logic regression. Okay. And if you look at 1 on GPA, and always assume 1 is the benchmark. That's the indicator that will tell you whether you're going to get an admit or not, or whether the results are going to be positive or not. And now this is more than 1, which means if you're having higher GPA and there are more chances that the probability of getting a positive result is higher, getting an admit is higher. And GRE, which is quite equal to 1, but does not, which means like it is not having much influence on your decision, but still it can have a positive effect on your results. Rank, which is if you're in rank 2 college, so basically you are having a negative outcome, right? And if you're in the rank 3 college, still negative. And then if you're in rank 4, the probability of getting an admit in the college that you applied is negative. Okay, because this is less than 1. Okay, so always remember when you're interpreting the exponentiated coefficient values and you benchmark that with 1, and if that is less than 1, you are going to have a negative outcome. The negative probability is going to happen. And if you're having a value more than 1, and you're going to get a positive outcome. Hope that clarifies. Any questions here?
One question, please.
Yes, please.
So we take the exponential of the coefficients, and then we compare or relate that to a scale to 1, right? So
Yeah.
1 means we have a possibility to get admitted. Below 1 means there's no possibility.
Mhm.
But then we see here the GPA is the most or the highest contributing factor. The higher the GPA, the more possibilities of getting admitted.
Yes.
And its value is 2.234.
Yeah.
So is it the maximum value possible in this for this data model?
Yeah. For this model, no, for the data that we have, and this is the maximum value, and it can also even go to 41, 31, based on the data that you're having, right? So, but with the data that we have, and it produces the parameter or estimates, which is 2.23, and it basically says that GPA has an higher impact or a higher impact on the decision. Okay, compared to GRE, compared to rank, and 2, 3, and 4. Right? And also, you need to remember that we don't have information for rank 1, and why it is not happening because the rank 1 is compared with rank 2, 3, and 4. Okay, so the benchmark for the model is rank 1. And imagine if they are all no positive here. Imagine, so if it is more than 1 or something, right? And still, which means maybe rank 1 either have positive or negative on the higher scale, and you're supposed to be careful in interpreting the data. But the benchmark will be always will be good as it serves as an indicator, and they are always in the positive phases. Okay, and this is the number of like when you might also ask, right? So why it is like 2.23, right? So which means like it has 2.23 times impact on your decision. Okay, so it will be it's a very nice indicator for you to say which of the variable, which of the predictor has more impact, and that can be decided with this number. Okay, I hope that clarifies.
Yeah.
Now let's get into the confidence intervals. Yeah, please.
Bala, one question. How does we interpret in terms of p-value?
Okay, so let's get into the summary. Okay. Let me go back to the basic stats, right? So basic stats says that, and as a researcher, you will normally set an error term, okay? And you will allow some sort of 5% error in the model. You will not allow more than 5%. So in general, like so, kind of it's kind of thumb rule, but it's not the case that should be always like 5%. It can also vary.
Yeah.
But however, and as a thumb rule, people set like 5%. Okay, so that's the estimate that the model, the system will also take. Okay, when you're trying to build a model, and the p-value is indicating the percentage of errors that you are trying to allow into the model. If it is exceeding the 5% level, which means your model basically have more errors, which is just not, which you are not trying to accept it, right? And that is not really permitted as a because it is set by you, it is not set by the system, right? And so that has to be taken into account. Imagine if you're having p-value more than 5%, which means that the error rate is higher, and also that means that predictor is not a good indicator for your model. So you are basically supposed to remove that predictor from the model and then build a new model. Okay, one is that. And second thing is that the p-value is also in order to understand it plainly, let me put it in a different context. And I normally say this example because it's really easy to understand. Okay, I think Swati might have heard many times because she also attends my stats class. So P is imagine that you're running a medical science study, and I think I told the same in the last class. I'm not really sure, but imagine that you're running a medical science study. Okay, so trying to create a vaccine for coronavirus. Okay, so it's a hot topic. It can be easily related, and you are giving this vaccine to 100 people. And as a researcher, you are saying that my error rate is somewhere around 5%. So what do you mean by that? You are saying that if I give this drug to 100 people, 5 people will die. Right? That's error rate. So the vaccine was tested and then you are allowing 5% error rate. So basically, if you give this vaccine to 100 people and 5 people will die. And will you allow it as a policymaker?
Yeah, I mean, it's lesser chances of death rate.
It's a bit tricky, right? So as for the
Yeah.
medical researchers, you cannot really allow much of the error rate, right?
Yeah.
Imagine if it is 5 for 100, it's going to be 50 for 1,000. And people will not accept it. So for medical researchers, the p-value or error term that is allowed is somewhere around 1%.
1, yeah.
1 out of 100 is okay. It's like even they will normally go for like 1 out of 1,000 because they don't want to they don't want people to die. Yeah. So that is how this p terms works. The p-value work. And the p-value is like normally the error term that you're setting. And the p-value is a good indicator whether your model is fitting well or not. And if you're having more errors in your model, and if you're having more errors in the model, it is not permissible. Okay, and this p-value is set by the researcher, but by default, the systems will take 5% values. You can change that one, if you want to change it. Okay, and you don't have to worry much. Why? Because you can also see the p-values are indicated here. If it is less than, is it like 10%? It's like if it is 0, sorry, if it is somewhere equal to 0, and always remember that the p-value is not normally equal to 0. If it is 0 here, it is not 0. It is 0.00000. Somewhere
Yeah.
you'll have 1. You'll have some sort of error rate, but it is very minimal and it is near to 0. Right? Here you are saying that it is somewhere around 0.001. It's like somewhere around 0.1% or something.
Yeah.
So 0.1% error. And here it is like 10% error, 5% error. Sorry, it is like 1% error, 5% error, and then this is 10%. Okay. I hope this clarifies what is p-value, right?
Yep.
Okay, so now it's time for you to work with another data that I sent to you, and I will stay here, right? So that I want you to interpret the data in a proper way.
Sure.
So you do all the coding, get the results, and identify the problems within the data, sort it out as well.
Okay.
Right? And anything that you want to get clarified, just let me know.
Sure.
Okay, so I'll allow you like 15 minutes time to complete the task, 15 to 20 minutes time, and I'll be back.
Sure.
After.
Yeah.
Yeah. Then we'll basically discuss the results. Okay.
Yeah.
Sorry, there is a bit of trick with the data that you got, and let me give you clarity on that. Right. So data. Try to look at the data. So most of them are in character form, right? So you can also use character data in model building. but you need to identify the dependent variable which has to be transformed as a factor, right? And transform that properly and then work on it. Okay, so Anirudhan, welcome back. I hope your internet issue is sorted. And we are working on the task 2, example 2. And people are trying to get their hands dirty in building logic regression model,
Okay.
the season pass.csv file. Right?
Right.
So you are given like 15 to 20 minutes time to complete this task and report the results.
Okay.
And I hope we don't really discuss much beyond what you listened. And if you have any questions, feel free to ask me. And I'm like taking a kind of break from the session. I'll be back after 15 minutes.
Okay, perfect. Thank you for the explanation.
See you in 15 minutes.
Bala,
Yeah.
you said something about the file, like character something.
Yeah.
Yes. I think it's all in factors.
Okay, so if it is factors, be happy, right?
Yeah.
So which is good for you, right? For example, say when you're reading CSV files, you can also set string as factors is equal to true.
Okay.
It is not happening. Sometimes in the case when you're reading CSV files, it may not really happen. Like they're all factors, right? And if it is not, if you want that all the character data to be read as a factor, and you can basically set, for example, say read.csv, and you can there's a code called string as factors is equal to true, and that will work. This is not working. Why? Because I'm not writing the code chunk.
Hmm.
If I write it in the code chunk, so for example, read.csv string, you see,
Channel and promo
then this
pass.
is true, and you'll basically avoid most of the problems. Yeah.
Pass, yes, pass.
Any other questions, Swati, or anyone else? Okay. If not, I'll take a break.
Yes, pass.
Perfect.
Mail bundle. Maybe I need to change it to bundle, no bundle. Email.
Bala, I think you're muted.
Okay. That's my bad. I mean, I'm audible now, right? So,
Yeah,
Yeah.
you're perfect.
okay. So now we have like three data, mm, three different variables. Okay, so pass is whether they will renew the pass or not. Okay, whether they will renew the pass or not is the is your is your DV. Okay, and promo, whether they have obtained promo or not, whether they are in the bundle offer or like whether they are not having bundle offer. And channel is like in what channel that they are coming. So they are they coming to the maybe any kind of resorts or any kind of theme park or something. Okay, this is about theme park, I hope. So for the theme park, and are they coming through email or mail, or are they just coming directly to the theme park and then collect tickets here, where they're buying bundle here or not? So bundle is related to the family bundle stuff. Okay, hope this clarifies, right? So now when your Venkat has done it, so which means now he has some sort of clarity. And Swati and Anirudhan, where are you like at the moment?
I have the I have the values estimates. I mean,
Okay, so you have the results, right?
yeah.
Okay, so let's see whether Swati has results. I am unmuted. Am I still in mute?
No, those are old messages.
All messages.
But I am getting it now. That's really bad. Okay, so not a problem. Say right. So let's get into the analysis part, right? Can someone send the code? I'll just copy and use it if you don't mind. Put it in the chat box. I'll copy and use it. Perfect. Okay. So
I'll send the.
got it.
Oh yeah.
Yeah. Not a problem. Not a problem. So it's like I need to work on it. And I don't normally use the bracket stuff. Okay, don't use that one. It might. I haven't really used that one so far, but that might be a way that it will work. Summary of model 2. Okay, so now you got the results, right? And tell me, how do you feel about it?
Well, so this data is a little bit funny because everything's a factor.
Yeah.
Everything's a binary more or less, except for the channel because there are like 3 different types of channels.
Mhm.
And it appears channel email has the highest chance because it's not listed in my coefficients data.
So channel email is not there.
Yeah, which means the channel mail and channel park are compared against to the channel email, right?
Yeah, true.
If I understand correctly.
Yeah.
So which means channel email has the highest chance, and compared to that, channel mail is compared to channel email, channel mail is 8 times or 8.8 times higher, and channel park is 41 times higher.
Okay, so I think you are getting the coefficients model, right?
I'm talking about the exponentials here.
Yeah, like let's first complete the summary of the data.
Sure. Yeah.
Then move on to this one. Like, let's start with the summary of the model. And if you can explain, what do you understand by the summary?
So I would say the promo no bundle has very high. No, wait. I'm understanding it wrong. Mathematics is a little bit rusty because it's been a year since I did mathematics. So
Like you don't have to do the math. Okay, system does the math. So you just have a look at the data and then just tell what you feel about it. Yeah.
No, I mean the exponentials and everything.
Okay, I understand what you mean. So like, have a from sorry, like my bad. My English is really getting worse.
Welcome to the club, actually.
Have a kind of rule of thumb. First, go for the p-values.
Yeah.
Okay. And now tell me, what do you understand by the p-values?
So I would say the errors are pretty okay for me because everything is higher or lesser than 0.05,
Yeah.
right?
So,
So it should less than 5%.
yeah, it means all the predictors are significant.
Yeah.
Okay. And they are able to predict the outcome of the outcome of the model in a very good way. So you don't have to worry much, right? Now let's go with the next part, right? Now let's get into the estimates. Okay. So the estimates, you can see there is promo bundle and promo no bundle. So whether they got bundle or they don't got bundle. Okay. And the promo no bundle is basically having least influence, right?
Yeah.
Right. And then what do you understand by channel mail and channel park?
Channel park has more influence
Yeah.
when compared to mail.
Yeah. And also you can see that is compared against email. So which means now we can see a trend which is increasing trend. In the earlier case, we got a decreasing trend. So the channel email may not have much influence compared to mail and channel park. You get what I mean?
Okay.
Yeah. So in the earlier case, when we looked at the model and we saw a decreasing trend, which means if you're from a level 1 college, you are getting the probability of getting admission is higher, but it is lowering down over the groups, right? But now you can see there is an increasing trend. And if you're coming to the theme park directly and getting a kind of a bundle, or it's like you're buying a ticket, and then the probability of getting the renewing the season pass is higher. Okay. And which is not the case with that is lesser with channel mail, and it's even lesser with email. Okay, so that is how you need to understand. Yeah. Clear? Any doubts? Any questions?
I have one question.
Yeah, please.
Is it possible to plot this? Because everything's a factor here.
Yeah.
And if
Can
we
also
do a
plot.
normal plot, it will just be dots everywhere.
Yes, you can do that. So basically, what you're supposed to do is like you do a ggplot with the data that you're having. Take your pass as when you're mapping, right? Next, map your channel as your x-axis,
Yeah.
and get a pass as the y-axis, and then and then try to plot it with geom smooth, or else like with even just try with geom point and geom smooth together, and then you'll get it. Okay.
Okay.
And
I'll try it then, yeah.
if you are trying to plot with the earlier case, like when you plotted with the normal functions for LMs, that might not really work with this logistic regression. That's another problem. Or else, like what you're supposed to do is extract channel email, channel mail, and channel park separately, and then for build chart for these three, and then merge them together. Now you'll get a results.
Oh, okay, yeah, that's a good idea.
Because you cannot really just perform with all the information together, extract them alone separately, and add like P1, P2, P3, and then you can just merge them together. So that's also possible. Right?
Thanks. I'll try it, yeah.
Yeah. So for example, say if you're trying to run a ggplot2, right? So ggplot, and you say my data, comma, AES of pass, and imagine that you extracted only channel email, right? And keep that one on the top, okay? And then go for geom and score smooth, and you write all the functions that is required, right? And later on, you can also work with another geom smooth, where here you can basically declare the data, the kind of minute, your new data, and then provide aesthetics mappings here, and then do similar fun stuff. Do you get what I mean?
Okay. Yeah, I understand, yeah.
Yeah, and then you can also add one more geom smooth. So
Yeah,
which will have three different
different, yeah, interpolations, extrapolations. Let's say.
yeah. Okay. So let's get back. Any other questions? Okay. If not, let's move on to this exponentiated coefficients model. Let's have a look into it. Okay. So what do you understand by this?
So the channel park has really high chances.
Yeah. So if they are coming to the park
Yeah.
directly and getting the pass, like in the early, like the season. So one thing that we are supposed to be sure is like when we get the data, and you should understand the data, because I did not really tell you anything about the data. So it is always becoming tricky for you to interpret the data, right? So as a data scientist, it is not that we know how to build models, and also we know how to interpret the data. You should be also sure about the context of the data that you're getting. You should really understand the nature of the data and the pattern of like. That's why you need a kind of a business knowledge, and also coding knowledge, and also kind of a statistical knowledge to do stuff. Okay. And now, since we do not really know much about this data, and we are struggling in terms of understanding how to interpret the data. Okay. So this is basically whether people buy season pass or not, and they observe the past behavior, and whether they went for a promo bundle or not a promo bundle, whether they got a bundle package or not, no bundle package. And also they got information like whether, how did they come to the theme park, whether they came through a mail promotion, or whether they directly came into the park and then got the season pass in the earlier case. And after that, there is one more information, right? So in terms of when you do take a summary, and where they came from the email and things. Okay. And these are past behaviors and past observations, which means like you're trying to predict the future behavior. If someone has a bundle and someone came through a channel park, and what should happen. Okay. And this indicates now if they are coming from a channel park, and if they did not really get a bundle, and the probability of coming back and buying a season pass is higher. Okay, so because now we can see we are trying to merge two information together to predict the probability. In the earlier case, we just said that okay, so if they are getting higher GPA, and if they are scoring a kind of a and they can get admissions in the university. But now we are trying to merge both information, like to have two predictors, and then we are trying to predict whether the outcome is positive or not, right? In out of the three categories that we had channel mail, email, channel mail, and then channel path. And out of that, we understand that channel park plays an important role. So if people come directly to the theme park, and if they got a bundle, or like if they do not really get a bundle, and the probability of renewing the season pass is higher. If in case, if the other case, that's going to be negative. For example, if they are not getting if they are getting a bundle package or something, and they are not really planning to renew your season pass. Okay. And we forgot to work on this confidence interval, right? Anyone know about confidence intervals? Exponentiated confidence intervals. What do you mean by this one? And this is really important. For you as a data scientist, you should also understand what is confidence intervals. Any idea? Swati, you should know because you learned this last week. Maybe I'm putting Swati into trouble.
Yes.
Yeah, tell me if you got some kind of idea about confidence intervals. Please throw some light so that Venkat and Anirudhan can learn.
Okay. I know, but I don't know how to explain.
Yeah, that's the challenge of any person, right? So maybe put in a plain understanding, whatever you understand. I think Venkat and Anirudhan, do you know Tamil?
Yeah, of course.
Venkat, do you know Tamil?
I understand a little bit, not
Okay,
much.
Swati, if you're fine, you can also say that in Tamil. எனக்கு ஒண்ணும் பிரச்சனை இல்லை.
Okay. This error, actually, confidence interval allows you to calculate the boundaries, the boundaries within which the population will fall. For example, let's take a weak student. If he is scoring an exam, if you check his, he will be scoring only within this interval, like from 15 to 45 or something. That's just his ability. So confidence interval is also an ability for the population.
Yeah. Okay, so thanks, Swati. I think you gave a kind of a very good overview of it. Let me explain as well. As Swati said, right, so this basically tells you the boundaries of the data. And you can see we cannot be really sure that that you are, for example, so let's get back to the coefficients model. The channel park has a kind of 41 times impact on the probability of renewing the season pass or not, right? That should be kind of varies, right? So not everybody is going to change, go for the season pass, but there will always be variations within the way that people are going to have an impact, right? So the variation can be captured with the confidence interval. So confidence interval is like how this impact can vary, and can vary from 30 to 56. And since the highest it can go is 56, because that's the extreme event, right? If the impact is even more, right, and that's kind of extreme case that's way beyond your imagination. And the least it can go is on the extreme end of the spectrum, which is around 30. So the variation of the data lies from 30 to 56. Okay, so that is the impact. Okay, so you cannot really always be sure that the impact is at 41 times, or it's like 41 percentage. So it can vary from 30% to 56%. Okay, and similarly for channel mail, and it's the same case, right? And also for promo bundle is the same case, where you say the promo bundle, if they don't get a bundle, right, and the probability is affected not at exactly at some point, like what we observed, not at exactly at 1.75, but basically it can vary. It can vary like from 0.46 to 2.19. So the parameter estimated is the midpoint of the data, and from the midpoint, and you can basically vary, right? And how can you say that? How can you get us an idea as a whether from the basic example? Imagine you're writing a math test, and you're writing it like for 5 times. And whenever you write the math test, if it's the same question paper, it's okay, but the question paper will also vary, right? And based on that, your answers will also vary, and also your scores will also vary. But in general, like with any question paper that is given to you, and you'll normally score in a range, right? You'll be basically falling in from like 60 to 80. And if it is given to me, basically I'll fall from 35 to 70 maybe, right? I cannot score more than 75, and that's my maximum score that I can go. But I'll barely pass, so I'll say 35. Right? So this variation is captured in the confidence interval. Okay, so this sort of difference is the max and min limit of any parameter is captured with the confidence interval. Okay, and the midpoint of this confidence interval is what we get from the exponential coefficient model. And from here, and how less it can go, and how max it can go, is captured by this confidence interval. So what is 2.5% here? 2.5% is the if you remember normal distribution curve that we discussed a bit earlier, right? And that's it, at 2.5%. And since we are predicting the data for 0.5% error, we are allowing 5% error, right? And if you're imagine that you're taking 100% as a base, right? You basically always take 100% as a base, right? And you're allowing 5% error. And the 5% error can be divided into 2. Why? Because always the normal distribution curve has two extremes, on the negative side and then the positive side. And what you're trying to do is like, and you're reducing 2.5% on both sides, both the tails. And if you remove that one, and basically you will have the data spread is from 2.5% to 97.5%, which means, and below 2.5% of the data, which means like it's the lower extreme cases, and above 97.5% is the higher extreme cases. They are all errors basically. Any data that is falling in between 2.5% to 97.5% is the true data. This is the thing that we are supposed to observe, and they will predict. That is where the scores are supposed to lie. And if you to know more about this, I'll normally recommend you to learn about central limit theorem and also understand about normal distribution curve. But don't worry about that at the moment. But this will basically tell you how your coefficients will vary and what are the extremes that can take. It can vary to 30, and the extreme it can max it can go as like 56. Okay, it is not a stable point. Okay, in terms of when you got 41.33, it is not the stable position, but it can vary from 30 to 56. Is it clarifying you now? Any other questions related to the model?
Not at the moment.
Not at the moment. Perfect. Thanks for your feedback. Okay, and if everything is clear, and let's wrap up the session today. And do you need any other data to work on for logic regression?
Yeah, Bala, if we have anything, please share.
Yeah, I think I have one. It's just kind of a proper ML data, machine learning data, and I'll share it with you. And if you're also so enthusiastic with data science oriented stuff, and you can also download from Kaggle. So I think you all know Kaggle. Right?
Kaggle, right?
Yeah. So Kaggle.com
Yeah.
and data.world.com. I think it's dataworld.com. I think should be there. And you can basically go and type like you want data for logic regression. But however, I'll also send you another data set in Skype, okay, which I used in the previous class. Okay, but the problem is like I may not be able to provide you the description of the data. And with Kaggle.com and dataworld.com, where you basically get description of the data as well. But I'll aim to provide description within Skype, and if not, try to just understand from the data, raw data, and look for the DVs and IVs, and then predict it. Maybe if you have any questions on that data, and then we can talk about it later on the next week. Okay, and with this information, and I'll say have a nice weekend, and we'll see you next week with cluster analysis.
Okay, perfect. Thanks.
Have a
weekend.
weekend. Bye-bye.
Bye.
Bye.